Great. Great, so we're ready to start this last lecture of the semester. Today we will see two parts. First, model predictive control, then application to demand response. So a few words about model predictive control. This is a technique that is used to provide control laws and is universally used in the context of smart grid. We will see an example in the context of controlling the customer size of consumers. In the lab, you will see you will have to use it for the continuation of the control that we have done of the small smart grid. Many of you have probably already heard or even used model predictive control. That will be very short, and we will focus on the technical difficulties that are very typical of the environment where we use it. So what is model predictive control? It's an alternative to find what we call policies. So remember, in the lab, in the first lab that you're doing, and what we saw last week, we saw that it's better to adapt to the current state of the disturbance rather than in advance pre-compute all the reactions. In the context of a smart grid, we had seen that the set points of the generators could be computed in advance, or instead what we could compute in advance is the parameters of a linear controller, and that led to what is called affine control feedback. We will see a different technique to address the same goal, and this technique will lead to an implicit control. So we will never know what is exactly the form of the controller. It will not be given by equation. It will be the result of optimization. How does it work? Well, first we assume the same model as last week. So we assume that we have a system that has a state at time t. Time is discrete typically. Xt is the state at time t. For example, that's the state of the grid like we saw in the previous weeks. Then we have controls. Controls are, for example, in last week, the set point of the generators. And we have the disturbance, which are, for example, the deviation from forecast that apply to the load or to whatever we are controlling. And we assume that we know exactly the dynamic system model. So we know the mapping that gives us the time dynamic evolution of the system if we would be able to observe everything without error, which of course we will not be able to do. But if we would be able to observe everything without error, in particular, if we can forecast the disturbance with 100% certainty, we would have a forecast equation for the state at the next time slot, if we choose, for example, the control action E. Of course, the problem is the disturbances are not known. We have a forecast, but they will evolve over time. And our job is to compute now, at time t, a decision, u of t, given where we are. This we typically know, although there are models that will treat the uncertain part of the state as a disturbance, and also will have the decision we have to take is done without knowing what the disturbance will be. So just before time t or at time t, we compute ut, but we don't know yet the value of the disturbance. Our decision ut and the decision of nature dt will lead to a new state xt. So that's the same system model we had last week. Now the technique to decide which action to take here is the following. At every time t, so we do it repeatedly, every time t, for example, in a smart grid that's operating as an energy management system, t would be every few minutes. In a smart grid that's controlling voltage and congestion on lines, t would be every second, or even in high-end systems like the grid steer one, it would be 10 times per second. So at every time step t, we observe what we need to observe with PMUs, for example, and we choose one control action ut. So that's not the MPC, that's just the name of the game here. What I forgot to say is, of course, we assume that there will be a cost associated to the decision that we have taken. And what we want is, as much as possible, to minimize the cost here. But that's the key point of MPC. We want to do it by taking into account the long-term effect. We will apply it here to a very simple example, simple but realistic example, which is controlling the heating system of a modern house that would be living in a place where the price of electricity is variable. So you have a house like this one. I use this house because this is there is all the technical details that are needed to do this model in this book that I give as a reference here, David McKay, Renewable Energy Without the Hot Air. That's a book that I highly recommend to all of you who are presumably interested in renewable energy. This is a very, very simple book that gives all the figures, the true figures and the true modeling values for any question you may ask yourself about renewable energy. So one of the questions is, if I want to do intelligent control of my house, I need a thermal model of my house. How do I do that? Well, here is one model. So here, why do we need a model? Well, because we assume here we manage space heating, for example, with a heat pump, it could be other systems, and the prices of electricity are variable. So what does this imply? Well, it implies that if there is a period of time where price of electricity is very low, then it's better to heat the house perhaps a bit above the set point. For example, this is a British house, so the minimum temperature is 19 degrees. Perhaps in Switzerland it would be 21. But we can live with any temperature that's slightly above, perhaps not below. So here we assume there is a comfort zone that is between 19 and 21 degrees C. And we also assume the house is well insulated, which is the case of David McKay's house, because this person is energy aware. So if the house is well insulated, it is a buffer. So it's like the battery we had or you are having that we have in the lab. We can store energy in the house in the form here of heat. And if at a given point in time, it's very cheap to generate energy because the grid price is low, or even better, because I have solar panels that are producing power for free, in this case here, then I can use this power at this point in time, heat the house a bit more, and then stop the heating when the prices are going to be high. So that's the principle. That's an example that will be used when we talk about demand response. When the customer is performing that type of actions, the customer is reacting to what the grid signals are being sent to her. So if the grid is instructing me, if the grid is sending me a signal that electricity is expensive now, then this customer reacts by consuming less. The model of the house is a model that dictates, that makes the relationship between our control action. Here, the control action is the amount of power that we use to run the heat pump, for example. And the state of the house is the internal temperature. Here, this model is simplified in the sense there's only one temperature. In reality, in the house, there are multiple rooms that may have different leakages. Maybe some may be exposed to the south with large windows, some to the north and be colder. So in reality, there would be an array of temperatures here. But here, to simplify, I'm assuming there's only one here. So the goal here is to see how the temperature of the house varies when I inject, when I buy some amount of electricity, U of t. Then there is this differential writing, which is the basis of our model. The electricity that I'm consuming here is translated into heat by a coefficient of efficiency, epsilon. That's the coefficient of the heat pump. So a good heat pump has a number between 2 and 3. It's generating more heat than the electricity that you put into it, because it's taking the heat out of an outside container. So that's the amount of heat that goes into the house. Now, where does the heat go when you use it for heating? There's no chemical reaction, so heat remains heat. So there's only two things it can do. It can go outside. It goes outside through the doors, through the cracks in the walls, through the fact that the walls are not perfect insulation. So this is captured by this first order model that says that the amount of heat that goes out during an interval of duration dt is proportional to the difference in temperature of the inside temperature and the outside temperature. by a coefficient K, which is the leakiness. So that is given for this house in David McKay's book here. So that's one part of the heat, that's the part that's lost, and the other part goes into changing the temperature. So if you heat up something, it becomes warmer, and that can be quantified. It's called the inertia. How many joules do you need to increase the temperature by 1 degree C? That the ratio here is given the inertia, and that also depends on things like how thick the material is, how big the house is as well. So the first one depends on the insulation. The second one depends on the mass of the house. That's the continuous time model. Now, because thermal systems vary very, very slowly, we don't need to really do partial differential equations. Simple discretization is enough. So if I replace dt by delta t, I go into discrete time. This is the thing I will have. So the difference in temperature here, that was dt before, becomes simply a discrete time derivative. So that's exactly the same formula that we had before. In this case, delta t is 1 minute, which for a heating system is probably already fairly fast. If I massage this, I obtain an equation that is in the form that I had as a generic form before. The temperature at time t plus 1 is a linear function of the temperature at time t, and of the control action that I took, and of the outside temperature. And in this case, the outside temperature is our disturbance. That's the thing we cannot know exactly in advance, but we're fairly able to predict here. So this is my system model. And my cost is, of course, the cost of the energy I'm buying here. We could stop there. We could put as cost the cost of energy. Very often when we do model predictive control or control in general, it's having hard constraints make the job more difficult. So very often we put soft constraints. So for things like temperature, we will tend to put a soft constraint in the sense that we have a temperature deadband, T min, T max. We put a penalty term that in this very simplified form is equal to 0 when we're in the comfort zone, and increases linearly with a given slope when we are outside of the control zone, of the comfort zone here. So it gives this formula. That's the max of 0 and 2 linear functions, T min minus T, this branch here, and T minus T max, this branch there. So this is a penalty R. We will pay a penalty for any deviation from that. And by putting this cost, this term here fairly high compared to this one, then except for very exceptional cases, we will make sure that we are always in the comfort zone here. So that is the framework. How does MPC solve the problem? Remember, the problem is now to say, I want to take the decision now such that in the long run, the collection of all my decisions will be close to optimal. So the idea is as follows. We observe the current state. We want to say something about the future, so we must have a prediction of the future. We have a horizon little h. H is, for example, in the case of a house, would be at least 24 hours. We will need to be anticipate a full cycle of the variation between day and night if the prices and the variability, because the prices and the variability typically follow a daily pattern. If you want to be more efficient, probably you would have to have a horizon of a bit more than a day. So capital H is the horizon here. We obtain a prediction here. And then we solve an optimization problem by assuming that the future of the disturbance will be equal to the prediction, and we compute the sequence of control actions that minimize the integral of the costs over the time horizon. That gives us a sequence of optimal set points here. But, and that's the trick of MPC, we will implement only the first of these control actions here. We implement UT. The others were computed, but they will not be used because in the meantime, before applying UT plus 1, I will advance my time. I will measure the state of the disturbance. I will compute the new state or remeasure the new state from direct measurement rather than from the state equation. And I will do it again. So that's the main idea of MPC. We do what is called a receding horizon control. We optimize over a horizon for the whole trajectory. This is illustrated here. Assume you want to drive a car. Your prediction is how the road looks like. The road is, of course, bumpy and does not always react exactly the way you would assume it. So if you want to drive an autonomous car in this curve here, you will compute at time t an ideal set of control actions that will lead to this trajectory. So that is what your optimizer has computed. And you will implement the torque, all the actions on all the elements of the car that will lead you to drive to some point. And at time t+1, you will not be at the point where you were supposed to be, but somewhere else, because there's a disturbance. In the case of a car, that's because your model of the road is not perfect. Your model of the car probably also is not perfect. So there is noise added to the real stuff. So when you are at time xt+1, you are here, which is not the same as there, then you will throw away the previous trajectory and compute another one. That is exactly what NPC is doing. But this example of a car here is illustrated exactly why we do an NPC. When I am at this point here, I know that there is a road that's turning on the right. So I take decisions that will lead me to this direction. So that's exactly the idea of NPC. When I drive my heating system, I know that the night will be coming, and at the night, I know, for example, that the temperatures will be lower, and perhaps there will be periods of the night where the prices are higher. So I know those things, so I know where I want to steer my control actions, but at the same time, I don't do a control once for all into the entire future, because I know also that there will be differences, and I take care of those differences. So an NPC is a way of controlling a policy, because given where I am, given my model of the state, and given everything I have observed, I compute an action here. But this action is not given by a simple control law, like you are doing in the first part of the lab. In the second part of the lab, we'll do exactly this here, where we don't know exactly what is the form of the control law. We have just numerically obtained the value of the control by solving an optimization problem. So let's apply this to our problem of controlling the temperature of the house. And here the goal is to have the electricity bill, which is as small as possible. That's the selfish goal of the consumer in this system. But the social goal is, if this is a smart grid that is sending signals to consumers, it is also having the effect of forcing consumers or incentivizing consumers to do the right actions, for example, to consume less when the grid has a hard time producing for everyone. So here, the disturbance is the temperature, so we must have a prediction of the outside temperature. For example, what I did is, in this example, I used historical prediction. Those are very cheap prediction. Today, in the context of smart grid, you have lots of services that will give you actual prediction based on today's condition, because that has becoming a very useful thing to do in, for example, running solar PVs or heating of industrial buildings. So this is becoming available. Then I have to minimize we have a stochastic optimization problem, like we discussed in the last lecture. Here I have to define what is my cost. Is it the expected? Is it the worst case? Here I take the expected cost. And for that, I simply assume that the future temperatures will be equal to prediction here. So that leads to the cost function that is given here. I minimize over all the control actions and all the states. The control actions are the control including now. The states start at the next state, because the states now I have observed it, of the price, the integral of the price from now to my horizon h. This is the price, the money price that I pay for the electricity I'm buying. And this is the penalty that we've discussed before here. So that's my objective function. The optimization variables are the control and the state space. And the state space equation we have seen a minute ago. This is the linear relationship that gives the state at time s+1 as a function of the state at time s and the control action and the disturbance. Here, when s is equal to t, the state T sub T is not an optimization variable, it's known, but all the other capital T's are optimization variables here. So here, theta hat is given in this optimization problem. This is my forecast here. So we pretend that the temperature will be exactly what it is said. So there is no robust part here. There is no whatever theta. We're not optimizing anything on the uncertainty of the disturbance. We'll talk a bit about that towards the end. Here we're taking the disturbance as completely deterministic. And the inside temperature will therefore, according to my model, will be simply a direct consequence of the outside temperature, which is an exogenous set of variables, my control actions. So it becomes also a control variable. I can control my internal temperature, at least in this model. The MPC believes in the model. Of course, we don't believe entirely in the model. It is like here. The MPC believes there will be the green trajectory, but in reality, we will reobserve things at time t plus 1, of course. And of course, there may be constraints on the control actions. Here, for example, on the heat pump, there is simply a min and max constraint. In other more sophisticated systems, there might be also ramp-up constraints like we have seen in the context of the previous labs. As I mentioned, the way we run this in the energy management system of this house is at every time t, so every minute, we observe the house temperature, compute the next action by solving this optimization problem, and then we simply implement during 1 minute a certain control action. This is a result of the simulation of exactly this house. So the parameters are given here. They are taken from exactly a concrete example. So those are the values you find. The heat pump has a large coefficient of efficiency, which means it's not an air heat pump, but probably it has a ground sensor. And the penalty function is very large here. It's equal to 1 franc per degree C of violation and per minute. So we think that the fact that during 1 minute we're outside of the comfort zone, that is worth 1 franc, which is very large compared to the cost of heating during 1 minute, but that's one choice that will lead to probably no violation of the temperature. Here's the result of one simulation. You see on the left, temperatures, outside temperature. The dashed lines are the prediction that were available to the MPCs. The thick dashed lines are the true realizations that, of course, are not known before ahead of time. And this is showing the room temperature, which is between 19 and 21 degrees here. We see here in orange the prices of electricity. In this example, they are assumed to be known. In some systems, the prices vary randomly. Here they don't. Here they're known. So you see that here we're at night. The price has a fairly low, but not very low, has a low value at night. Then there is a morning peak where prices double. Then there is the middle of the day where prices are at a medium value. And there's also a low at lunchtime. This is probably because this is a region where there is solar energy. David's house is in Cambridge, and even in winter in Cambridge, there is solar energy. So this is a period of time where prices are low. So those are the prices here. And let's see how the MPC has reacted. In the middle of the night, the temperature was the lowest possible. And we see that the MPC is anticipating, so during this period of time, the prices are very low, but here the prices will be high. So the MPC is anticipating that the prices will be high, and it does it at the last minute, as lately as possible. It was not putting the temperature to 21 degrees during the whole night, because electricity is cheap. No, it knows exactly how much time it will take to raise the temperature from 19 to 21, and it does it just before the high prices value here. So this is a form of storage. During this form here, we have stored energy into the house. And when the prices becomes very high, we don't heat the house. We see that the temperature goes down. We see, in fact, that we don't heat the house even at the middle value here. So the MPC has taken the decision implicitly, we did not write a rule into the MPC, just the result of optimization. The MPC has taken the decision that it will heat the house maximally at the end of the night in order to escape the peak and the middle average values of the early morning. And then, as soon as there is a very low price here in the around lunchtime, it heats up again and stops when the prices become large again, and then goes down. And here it is forced to heat at a medium price in order to avoid the next peak that will come, etc. So that's the trajectory that the MPC is doing. You can see this sawtooth behavior that you can explain after the fact, but the good thing about the MPC is that nobody had to analyze everything I'm saying here. We just put the cost function, the system model, and the MPC does the right thing here. We see also that the day 2 and day 1 are very similar, but are not the same. We see that, for example, at day 2 here, the decisions that were taken led to slightly different state of temperature here, because the outside temperature were different. So this is an illustration that the MPC is taking decisions that may vary based on the actual implementation. So it adapts the MPC forecast, but also adapts to deviations from forecast. That's the price that we paid for 1 day, 5.8 francs. If I compare to what you would do if you don't have an MPC in the same setting, you would put a thermostatic control. What is a thermostatic control? Well, this is a thermostat is something that has a comfort zone, typically a much smaller comfort zone. So here it's between 19 and 19.5 degrees, and it will heat the house until it hits them outside the upper bound of the thermostatic of the what is called the dead band. Then it will stop heating, etc. So that gives this iterative system. We see that the shape is slightly different. That is due to the outside temperature. When the outside temperature is large, then the leakage is smaller. So when we reach the higher possible value, it takes a larger time for the house to cool down. So this, of course, has no knowledge of the price here. So it simply keeps the house at the constant temperature. And the cost, as you see, is considerably larger here. So the MPC was able to anticipate periods of high cost and could adapt to the cost. So the MPC can be used in a general way to selfishly optimize your resources, but also as a way to control in a distributed way the energy system of a given country or continent. Voilà, so that's the only thing we'll see about MPCs. There are variants of MPCs. There's a lot of literature on various things you can do with MPCs. But the beauty of it is that with these very simple things that I've shown, you have 95% of the story of MPC. And you can control energy systems, smart grids, and a large number of other systems as well. Now, when we do this, we will have to do repeated solution of an optimization problem. So the downside of MPC is that it needs to solve optimization problems fairly fast, perhaps not in real time, although some systems are quasi real time, but you will need to do it very fast. So you need to have optimization problems that are relatively tractable. In practice, many MPCs are linear MPCs. So we will see how to continue. This is a continuation of the theme we saw last week. How do we transform an optimization problem into one that is more tractable? That's something that is perhaps less well known, but in practice, as soon as we have to do an MPC in the context of an energy system, we are confronted with this problem. We have seen examples already. We have seen how to remove a max, for example, from the objective. We have seen how to remove quantifiers. So let's continue with one or two little things in the same direction. Let us start with a small drill on mean, on max. I'm proposing here two formulas. I have a function of two variables, x and y, where x varies in a state capital X and y in a state capital Y. I maximize with respect to y, then I take the minimum of that, or I do the other way around. I do the same I want to have the X that minimizes and the Y that maximizes, but I do the minimization in X first. Is there a difference in doing any of this? I close the poll in a few seconds. Closing. And the majority says B. It's the same, but it is not. So that is the bad news. Min and max are not good friends. You cannot simply change the order. Here's perhaps an easy way to remember why. Assume I have on a chessboard mice and elephants. Right. The x-axis is a coordinate of my chessboard, the y-axis is another coordinate. And the f of xy is the mass of the animal that is at coordinate xy. Assume, to simplify the story, that on every column there is at least one animal of each type, and same on any row here. So what do I do when I compute A star? I maximize over y. So y is this coordinate here. So what do I do when I maximize over y? That means I pick an x, for example, this one, x equals 3 in this case, and I maximize over y. That means I look for the weight of the largest animal on this column. Well, it is an elephant, because by our rule, there is an elephant on every row and on every column, and also a mouse. There are small elephants, there are big elephants, but certainly the larger one is an elephant, because even the smallest elephant is larger than the largest mouse. So when I compute the max over y first, I obtain an elephant. And then what do I do when I take the mix? Well, the mean. Well, for every value of x, I have computed which elephant gives. I select from this. I take the largest elephant of every row, and then I take the mean. So A star will be an elephant, will be the weight of an elephant. Conversely, if I change the order, I start by, I fix y, for example, here, y gives me this row here, and I look for the mean. I pick the smallest weight, well, it's certainly a mouse, and then I take the largest of the mice here. So B, through the first operation, gives me always a mouse, and I take the max of the mice, it's always a mouse here, whereas A always returns an elephant. So at least in this example, A star will always be larger than or equal to B star. Well, this is in fact always true, even if I relax the conditions that there must be an animal of every type on every row and every column. It's always true. Sometimes there can be equality. There could be equality if I relax my condition here. If there would be a row with only mice and a row with only elephant, for example, that could, in a column with only mice, and there could be equality. But certainly there is always this inequality, and in general, we expect A star to be larger than B star. In our case here, it will be strictly larger because an elephant is always larger than a mouse. So this has a name, it's called the Max Mean Inequality. Oops, this was the animation I want. This is not unrelated to what we saw before. For example, if you remember our optimization duality discussion of last lecture here, then if we replace the original optimization problem by the Lagrangian here, when I solve the unconstrained optimization problem, I compute the minimum over x for a given lambda and nu. Lambda and nu are the Lagrange multiplier. By solving this, what I'm doing here is solving the unconstrained problem that is derived from the Lagrangian. And duality says that I take the max of this, and that gives me the value. The optimal value of this is called the dual function, and the dual problem maximizes the dual function. So that gives me the dual here. It can also be seen that the original problem leads to the same here. Solving the unconstrained problem is the same as first maximizing over the Lagrange multipliers here, because here you add a penalty for the constraint. So if you want to minimize it, you make the constraint true here. And the mean max, the max mean property says simply that D star is less than or equal to P star. So the weak duality that we've seen before is exactly this. In general, we know that there is not equality, except when strong duality holds, which is when we have a special case of min and max. Why do we care about that? Well, the theory of duality, you can ignore it, and as long as you handle it properly. But what you cannot ignore, what you must handle properly, is avoid to make mistakes, because we will constantly have in our optimization problem, we will have min and max. For example, we've seen already last week, you've seen in the quiz that when we have piecewise linear functions, that leads automatically to min and max, also when we remove quantifiers here. So being able to do it right is exactly the topic of what we're saying. So here's a second quiz, second question. Same as before, except now I have min and mean on one side. So I simply change the order. I minimize with respect to the y index, the index of the column, of the row, or vice versa. What do you think is true? I close the poll in a few seconds. And the majority says B, which is the correct answer. If we first select the smallest mouse on every row, then select the smallest of the chosen mice, then we obtain the overall smallest mouse. Right? This is also a principle called divide and conquer. If you want to compute the minimum of a large set of things, you can partition your set, choose the minimum of every subset, and then compare the minimums, and etc. This is it, and this works. So the mean in this order is also the global mean. So those three notations are equal. Here, that means I treat the variable xy as one variable, and I ask what's the smallest of all. Then it is the same as this divide and conquer things I said before. It's also called the associativity of mean. If instead of mean I had plus, if I had addition of things, then if I had a sigma, a summation sign here, that would be the same here. So, and if I have an integral, we know also that a double integral, you can integrate with respect to one variable or the other. Of course, you need to make sure that the constraints are satisfied, but here I was assuming the constraints on x and y are independent. So this is called the associativity of min. It works also for max, of course. So the good news is we can mix and match mins, and the same for maxes. But remember, as we saw before, mean and max are not good friends. They are like cats and dogs. Putting them together requires some care. But as long as they're of the same kind, they play together well. So let's apply this to the concrete kind of problems we have when we run or develop an energy management system. It is at the end of the day, go from our modeling, this is the modeling I did here, into an optimization problem here. So here we've seen this model for controlling the temperature in my house. This is the optimization problem I have. Here I'm proposing two formulations as MATLAB implementable optimization problems. Which one, if any, is a valid implementation? I close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. Here is a straightforward application of what we saw in the last lecture. We have an objective function, which is of this nature here, where phi is itself a max here. So we have this function here. So the trick, which should be familiar to you now if you've done all the quiz, is that this is the max of those three functions here. One linear function with negative slope, 0, and a linear function with positive slope here. Sorry. Therefore, we can use the max removal transformation. We have seen that if I have to minimize an objective function, that is a sum of terms, some terms being themselves the max of several things here, then we can replace every max by an additional optimization variable and add the constraint that this optimization variable must be an upper bound to all the members of the max here. So this is what I'm doing here. I replace one of those terms here, for example, phi of t1 plus 1 by an epsilon t plus 1, and I add the constraint that epsilon is less than the 3 terms of the max function here. So that gives exactly formulation B. Formulation B is this one here. There is one epsilon s in the summation. So that's good. Now let's see another frequently used formulation of MPC. Like in stochastic programming in general, the issue is here what costs we take. We've seen that we can take the expected cost or the proxy for the expected cost or the worst case cost. So depending on the setting, depending on the taste and the tradition also, we take one or the other. Here, let me assume that for some reason, I care about the penalty. I want to reinforce that I don't want the penalty to be violated here. So I add a penalty that is perhaps with a larger function and is the max. So if during only one time slot I exceed, then I will pay the penalty. So instead of the integral, I take the max of the penalty. If I do this, Why not? It's a bit more complicated. And, of course, if you do that, you have to change the value of phi, because a single violation you might want to penalize it more, given that if you violate it 10 times or once, it gives the same. So here you insist really on never violating, whereas before you insisted on violating not much. Right? But now the technical question is, how do we translate that into an optimization problem? So again, same question as a minute ago, same quiz. I have this variant of the formulation of my optimization problem. I propose the two implementation that we saw before, the implementation B, another one here. Is any of these two or both or an equivalent to a correct implementation of this problem? I close the poll in a few seconds. Closing. The majority says A, which I think is probably easy to guess. The interesting question is how? How do we translate this? How can we convince ourselves that this corresponds to A? Well, we have now all the technical means. The objective function, the cost function as is given here, has a summation part. This one doesn't pose any problem. Plus it is the max of the penalty. So I rewrite here, that's the max of the penalties. And each of the phi of TS is itself a max of three things. So this is where now I use my results on associativity of max. It's a max of max, so it's a global max. It's the max of all those terms when I put them all in a bag. So I take all those terms for all possible values of S, and I have simply the overall max of that. So I have an optimization function, which is of the form some term here that I will keep unchanged, plus a max. It's a big max. It's a max over all S and all I of this expression LIS, which is the expression given here. So I can write it in this form. Now I can apply what we've seen many times, the removal of a max, but here, since there is only one max, there is only one epsilon. So I minimize over all the control and state variables we had before, and over one penalty term epsilon here, while I add the constraint that epsilon must be larger than all those member terms that are here. That gives exactly this, sum over epsilon, epsilon's larger than this for all terms. Voila, that's the key thing. The important thing that I wanted to share with you and I wanted you to be aware of is to be able to make the difference between the two. So very often we go very quickly from this to that without making it explicit. What I hope to have done in this lecture and in the previous one is given a number of rules that allow mechanical transformation from terms of optimization problem into other ones that will be manipulable, easy to manipulate, that will be because they will be linear. We come to the end of this first hour. So MPC uses the techniques of optimization plus a receding horizon. It applies to control energy systems with storage in particular. And so that's really the method of choice that we will find in all such systems. With an MPC, we obtain an implicit policy. A policy is a method that gives the control action as a function of what we have observed. as opposed to a predefined control rule. It's usually nonlinear, and in general, we don't know, we don't have a closed form for what it does exactly. And the major difference compared to the rest is that it looks ahead. And this is why, because it looks ahead, that of course is very good for storage system. So if you know that a bit about the future, you know what you will do with your energy that is stored or needs to be stored. In practice, when we do it, we've seen that we may need to be experts in transforming optimization problems. That should sound familiar. And we have seen an additional set of problems that arise when we make the problem more complex, like we do with MPC, which is in particular the combinations of mean and max here. So when we have mean and max together, red flag, be careful. When you have means together or max together, that's easy. We can just associate in any order that we want here. Last, MPC is very, very much used in the context of energy system, but also in other contexts, in control of any industrial system, because it's very robust, because the robustness comes from the fact that we take a decision now based on us looking into the future, but we will revisit this decision as soon as we have new information. Because of that, it's robust. If we want to be even more robust, then we can use the techniques we've seen before with robust techniques, robust programming. So if we think that we have not just a prediction of the temperature, but also prediction intervals within the temperature will be between these and these bounds, then we might have a more conservative MPC here. And we can also use scenario-based programming, but this year we don't see these techniques because we had to skip one lecture, and we will have enough to do with what we're seeing today. Voila, that's the end of this first part of the lecture. We do a break in about 10 minutes. So at 10:15, we will restart and start the last module on demand response.